There's only so much that a math teacher can do to explain why the chain rule is true. I mean, this is the way that chains work in real life, and that's kind of all there is to say about it.
So if it's like a piece of metal and it has like teeth and it fits together, it's a gear. But if it's like a piece of metal and it has teeth and there's a chain that goes around it, we call it a sprocket. So these are supposed to be sprockets. And so they're supposed to be chains that go around them. And I put the radius of each one of the sprockets. So let's go ahead and name them. I'm going to call this one up top Z, and then this one in the middle X, and then this one at the bottom U. So when you rotate the gear U, since its diameter is bigger, that's going to cause more rotations to happen in X. In fact, since it's a 6-inch sprocket and a 3-inch sprocket, the gear ratio is 2-to-1. So that what that means is that one revolution down here in U will cause 2 revolutions on the X sprocket. So what that means is that each small change in U will have to be multiplied by 2 in order to calculate how much change there will be in X. In other words, 2 times du is equal to dx. Or if I wanted to just write, 2 times du is equal to dx, or another way to think of that is dx. You can see if I divide both sides by du, I get dx du equals 2. So I'll write that down. Dx du equals 2. And then since this gear ratio at the top is 3-to-1, this means dz dx is equal to 3. So I think if you look at this picture, you can see what will making one revolution, how many revolutions in Z will happen if I make one revolution around U. Can you see 6? It's going to be 6. So what this means is dz du is equal to dz dx times dx du. And this seems all well and good. This is what you learned in Calc 1. But what this leaves out is what can happen when, you're riding on a bicycle built for 2. What if Z depends on more than just the variables X and U? All right, I'm going to have to abandon my bicycle built for 2 analogy. I was trying really hard to make it work, but it's just doesn't quite fit perfectly because there's 2 people. What I really want to do is consider the case when Z depends on X and X depends on U. And then also Z depends on another sprocket Y, which is also being turned by U. So this is the interesting case that we want to study for math class. And what's going to happen in this case is the total amount of rotating that's happening in Z. As you turn U, that's going to spin both X and Y. And then the amount of spinning that's happening in Z is just going to be the sum of the amount of spinning that's happening in X and the amount of spinning that's happening in Y. So the final formula that we get is del Z. See, I can't write D anymore because these are partial derivatives. So del Z del U is equal to del Z del X times del X del U. That's how much spinning is happening when U turns, and then that turns X, and then that turns Z, plus how much spinning is happening when U turns Y, and then Y turns Z. So this will have to be del Z del Y plus times del Y del U. So there it is. This is what we use as the chain rule in when the functions are of multiple variables. One thing that I want to point out is we are tempted when we start making statements about a small change in this and a small change in that to just like use our regular old rules of algebra. And this is an example in math where that is a mistake and that would give you the wrong answer. You can see if I start canceling out these del x's and canceling out these del y's, then I would actually have two del z del u's on the right hand side and just one of them on the left hand side. So be careful when you're working with these like partial derivative symbols and stuff. These are defined as limits of ratios, so you can't just go like adding and subtracting and multiplying and dividing as you usually would with variables. So the way that we understand the chain rule, kind of like the simple mnemonic, just to put it in our brains, is you find all the paths and you multiply along the path and then you add up all of the paths. And these pictures that you create like this, where the variables are, we think of them as like sprockets. They're called dependency diagrams. Usually students catch on to this really quickly. Let me do an example that has like sufficient complexity. So here's an example. In this situation, we have the variable w, which depends on x and y and z. And then x is some function of u and v. Y is some function of v, and z is like x. It's a function of both u and v. So I'm just going to start by kind of making a tower of variables. At the top, I'm going to put w because it depends on the things below it. And then w depends on x and y and z. So that's the next level. So w up here, x, y, and z. And then there's just two variables down below, u and v. And then so now I'm going to draw a line each time one of the variables depends on the other variable. So w depends on x and y and z. All right, now x depends on both u and v. Y only depends on v, and z depends on both u and v. So you basically just draw a line where whenever one of the variables depends on another one. And then what goes on these lines is the rates of change. So in this case, this line right here would be del z del v. Be careful with this though, because this line right here is actually just dy dv, because y actually isn't a function of multiple variables. It only depends on k. So let's use this dependency diagram to calculate one of these chain rules. All right, so I'm going to calculate del w del v and del w del u. So first, I need to find all the paths that lead from v to w. So I can get from w up to v by going through x. I can get from w up from v up to w by going through y, and I can get from v up to w by going through z. So there's three paths, so I'm going to have three things added together. So the first path is going to be del w del x times del x del v. So that's this path right here. Okay. Now the next path is going to be del w del y, and then del, okay, so del w del y, and then now y is actually just a function of one variable. So this is actually going to be dy dv. And then there's one more way to get there, right? I can go through z like this. So del w del z, z times, and then del z del v. Okay, so there were three paths from w to v. Let's do del w del u. I think it's actually going to be more simple. Let's look. How many ways are there for us to get from w to u? So I can go this way through x, but actually there isn't a path through y that leads there. So I can go from w over to z, and then from z down to u. So I'm going to just do del w del x times del x del u plus, I can go through z, del w del z times del z del u. I'm going through z down to u like that. So that's the way the chain rule works. You know, if you're kind of waiting for the other shoe to drop on this, don't. This is really as complicated as this picture gets. I want to just show you an example where we do this in a really basic way because we're not really here. You know, the chain rule isn't the end goal of this. The reason that we're learning this is because it's going to help us answer that question from the last video about calculating the derivative if we move in any direction. So here's a problem where z actually represents a surface that sits above the xy plane, and then x and y both depend on t. Oh, I've been a little bit of a bad teacher here. Z really is a function of multiple variables, so this should be del z del t, and I should fix these as well. So del z del t. And then hopefully you can see here that I'm just using my little dependency diagram to just find all the paths from z down to t and then multiply along the paths and then add each one of those paths together. All right, so let's work out del z del t so we can just see how this example plays out. So this is, if I do del z del x, that's the partial x derivative of this, I'm getting 14x times dx dt, I'm getting 3, plus del z del y. If you do the y partial derivative of this, I'm getting -6, and then times dy dt. So y is 4t, so dy dt will be 4, which is 42x minus 24. But since I'm calculating del x del t, I really want my answer to be in terms of t, which is kind of a bummer because there's another Hitchhiker's Guide to the Galaxy reference. But it's not going to be, because now this has got to be 42 times x. X was 3t, so this is going to be 42 times 3t minus 24, which is 126t minus 24. So there it is. That's how you use the chain rule in this example. I just want to give a little bit of geometric context to the problem that we actually solved. The geometric interpretation of z is a function of x and y is that z is a surface in 3D space. And then x is 3t and y is 4t. That's a line in the xy plane. So one way to interpret this information geometrically is to imagine being standing at a point, and then as t increases, we're gonna walk along the line. And what we're calculating here is how z changes as we walk along that line. So if we imagine ourselves at a point right there on the surface, and as t increases, we move along this line, so that means the point is going to go some way in that direction. And how much the height is changing is what we've just calculated right here. And that was the goal. That was what we set out to calculate last time. And I'm going to get into it more in detail in the next video. But before we do that, I just want you to look at this formula right here, because this happens all the time in math. You're doing something, and if you just take a minute to look at the formula, you're going to realize that it's actually a dot product. And it is. This is a dot product. In fact, this formula, del z del u, if I wanted to, I could write it like this. Del z del x del z del y dot product with del x del u del y del u, right? Because that's the way the dot product formula works. You multiply these together, and then you add them up. And that's exactly what this chain rule process did. So, wow, we have kind of stumbled across something that's really cool here. I just want to point out at this stage that this thing right here does have a name. And this is, the point of this conversation is to talk about this object right here. It's called the gradient, and the symbols that we would write for this is you write an upside down triangle and then a Z. And what I like to do in the next video and the preceding videos is to try to convince you that this object, which is a vector, is the correct higher dimensional generalization of the derivative.